And can you see my
Perfect.
screen?
Perfect. It's online, made by Alejandro Bermúdez from Madrid. And he'll tell us about synthetic HVs and trapped ion crystals. Alejandro,
Hello, just 1 second. Can you see my screen now? Just give me a second.
Can you speak?
There we go. Yeah. Can you
Yeah.
listen to me? Perfect. Well, good morning, everyone. I would like to start by apologizing for not being there. I would have liked to join you there in Constance, but I had some family issues that avoided me being able to travel. So anyway, I would like to tell you about some of our recent works regarding the quantum simulations of gauge fields in trapped ion crystals. So this is a work that has spanned a few years and involves several collaborators. So I will start by reviewing very briefly how you can use this chains of trapped ions to simulate the physics of essentially charged particles. So this would be like quantum Hall effect physics, where you have like a background gauge field. So this field is completely static and homogeneous. And then I will tell you how you can, using similar ideas, you can move on to actually give quantum dynamics to this field. What you have to give in the way is that you go from the standard Maxwell electromagnetism towards something simpler, and this changes the gauge group from U1 to C2. So as I said, this is the collaboration of many people, and the most recent things I've been working with regarding C2 gauge field theories that I will be talking about is working in collaboration with the experimental group of Oxford led by David Lucas, and then the group of Luigi Amico in Abu Dhabi, and working with Enrico Domanti. So these are the works of the things I will be telling you about, and let me just briefly sketch what will be the contents. I will start by motivating, then I will go to telling you how you can use flow engineering to simulate a Payel's phase for phonons, essentially in these trapped ion crystals, and then I will move on to the real new results on C2 gauge field theories. So the motivation comes from the quantum simulation business. So there are complicated quantum many-body models. In particular, when you think about high energy physics, there are strongly coupled quantum field theories that you might want to, understand, for instance, by putting them on a lattice and studying things such as the phase diagram of QCD, or you might be interested in studying, real-time dynamics, which is also very complicated. So the idea then goes back to quantum simulation paradigm of Richard Feynman. So instead of using classical computers, you would use a quantum system that is highly tunable. So this idea has been around for many years, but in around 2012, this is where all the applications to quantum field theories kind of saw an increase in interest, and this was due to a paper in the Preskill group and also in the group of Virac and the group of Zoller, where they essentially came up with explicit proposals to simulate the interesting quantum field theories, such as non-abelian gauge theories in the case of the European groups. And in the group of Preskill, actually was more to the, understanding the complexity of what would be simulating real-time dynamics of the simplest field theory, that's a 5-4 field theory, and they were able to show that computationally it laid in the same complexity class as, the factorization, so source algorithm. Here are some reviews that you might want to check if you want to have an update of what the field is doing. So I will tell you about what we have been working on in Madrid, and in collaboration with these other European groups. So essentially, this is the right. So we want to go from highly controllable systems, in particular atomic, molecular, and optical setups, and we want to go all the way to simulate gauge theory. This is complicated. In principle, we would like to go and simulate 3+1 Yang-Mills theory, so to understand the standard model. And there is a long road where you would like to be, hitting this very nice phenomenology of asymptotic freedom, anomalies, confinement, and these kind of things. But this is obviously very complicated. So actually what I will be talking about in this talk is let's start playing with only toy models that do not allow us to test all of these phenomena in full glory, but actually they have analogies with those phenomena, and you can target some of them in simpler setups. So this brings me to trying to discuss gauge fields in as background gauge fields on matter, on electrons that are in a lattice, and they can tunnel in the lattice. And actually, this goes back to flocked engineering and a phenomenon that is called coherent destruction of tunneling. So essentially, when you have electrons that are tunneling freely in whatever lattice, you just subject them to an oscillating electric field. Actually, this you represent in the Hamiltonian picture just as a gradient, but now this gradient is periodically modulated. And you can prove that when the tunneling strength is much weaker than the this electric field strength, essentially you can get like a description of the electrons as address Hamiltonian, where the tunneling is modified by a Bessel function. So essentially, just by coherent drivings, you can reach a value of where this Bessel function is 0, and you can coherently destruct the tunneling. So you stop the electrons from moving in the lattice, right? So the idea we had some years ago, together with Diego Porras in Madrid and Tobias Schatz in Freiburg, was that you could generalize this scheme, and instead of using a periodically modulated gradient, actually you have a purely static gradient that inhibits the tunneling, and now you start assisting this tunneling. But now what is very important is that this periodic modulation with which you will re-assist the tunneling, actually it comes from a plane wave. It's not just a DC potential. So it has an inhomogeneous phase. So you can then go through the same analysis. It's very simple to show that in the dressing of your effective tunneling of your electrons or your fermions or whatever particle, actually doesn't matter the statistics, tunnels in your lattice, actually it picks up a net phase, and you can use this phase to mimic the effect of a background gauge field. So this is a very important concept. Essentially, when a particle is tunneling from site J to site I, in order to make it gauge invariant, actually you have to introduce in between something that is called a parallel transporter. So it's just the exponential of the line integral of the vector potential. It's like the Aharonov-Bohm phase, right? So if the path now is closed, you can relate this line integral to the flux of an effective magnetic field. And with this, what you're making is you're making your particles, even if they're uncharged, they're behaving as if they were charged under a background gauge field, right? It's completely static and homogeneous if you want. So it gives you access to simulate quantum Hall physics. As I said, this is very generic and it applies to any statistics of particles. What we worked out in those papers back in the day was to apply this to trapped ion systems. So in these systems of trapped ions, so here you can see like a picture where you have DC and AC electrodes that confine your particles in a certain configuration. Typically, they form crystals, what we call Coulomb crystals. So here you can see, for instance, a trapping potential that is double well, and in these 2 points, it would be just 2 ions that are trapped at this position. So they are trapped and they form a crystal and at equilibrium, but actually they can vibrate around the equilibrium positions. And since they are charged particles, they will field the long-range Coulomb interaction, and the effective description for these vibrations is actually just that of a you can think of them as just dipole interactions. So it's you can get like a type binding model for the bosonic excitations. So the vibrations of the ions, the quantized vibrations, they can tunnel from site J to site I via dipole coupling strength. And actually, a very nice feature of this, some of these traps, these micro fabricated surface traps, is that actually the parameters of your system, they allow you to describe these effective dipole interactions in terms of a particle conserving Hamiltonian. So this was also realized by Diego Porras and Ignacio Cirac back in the day. There is a certain regime where actually there is a U1 particle conservation. So you can start thinking about these local vibrations really as bosonic particles with a well-defined conserved number of particles. And actually what you'd like to do now is to put a phase to these tunnelings so that they behave as charged particles. So now what we realize then is that you can, the effective action of this plane wave that I was referring at the beginning, you can engineer it by playing with essentially AC star shapes that come from 2 laser beams. And now there will be a bit node that has a certain frequency of your laser and a certain frequency wave vector difference. And now you can play with it in order to realize this flocked engineering. You get an effective phase, and you can play with it in order to make them behave as if they were traveling around, subjected to an effective magnetic field. So the simplest configuration that you can think about is a triangular crystal, where you have now 3 ions, and now when the phonons, they want to tunnel from one side to the other, they see effectively this Piles phase, and they behave as if they were seeing a transverse an effective magnetic field. So what you can prove is in the experiment is something similar to what would be a run-of-bone interference. So it's not the same if now I start driving my system and I create an excitation over this side and that side. So these are ions that they are heated by a coherent drive. So they are in coherent states. And now they will want to tunnel to the orange side, but they see a phase. So when this phase is 0 or is pi, there can be either constructive or destructive interference. And this is what they saw in the experiments. So this is a proof that actually this Floquet driving scheme is working in the lab, and they would like them to go from coherent states really down to T0 experiments where you have a single phononic excitations, and you really see even the circulation of bits and all of this kind of dynamics, okay? So this is very nice, but this is completely, it's still very far away from what we intended to do at the beginning, because we really want to go to gauge field theories. So here, these effective gauge potentials or the effective fluxes, they cannot just be background and fixed by whatever parameter in my experiment. They actually have to be quantum dynamical, right? So what I need to do now is in this tunneling of my particles, in this case it was bosons, right? The phonons of my crystal. I need to introduce a parallel transporter. Now depends in a sense of on a vector potential that is a quantum field, right? So it will depend on space and time, and it will have its own dynamics, right? So you can think about this in exactly the same picture as if I had electric and magnetic fields as operators, and they have to have their own dynamics. So if I have a U1 theory, this would be Maxwell electrodynamics, right? So I have the typical Hamiltonian description, which would be like E squared plus B squared as a Hamiltonian, and this gives dynamics for my electric field and my magnetic field, and this, it just goes back to my particles tunneling in my system, so there can be back action when my particles tunnel and interact with the electric field. Obviously, this is very complicated, so what we trade off is this U1 symmetry, and we go to something much simpler that is still kind of interesting, and it's the C2 gauge theory. So as I go back, and then the important ingredient is that my gauge fields, now they will be quantum, and they have to live in the links of my lattice. And instead of caring about a U1 symmetry, I will focus on a C2 symmetry, which simplifies very much the nature of this parallel transporter, because it can be just a qubit, essentially. So this is the typical setup of the C2 gauge theory, just with gauge fields now described as spin 1/2 particles. So it's, C2 gauge fields, essentially, and they are described by qubits that live on the links of the lattice. So I place my gauge fields on the links of a square lattice, and I define a Hamiltonian that is very similar to the E squared plus B squared term of Maxwell electrodynamics. It has an electric field term that is proportional to the Pauli matrix X. It cannot be X squared because that's identity. So this is why it just comes being linear in X. And then the magnetic field term is slightly more complicated. You need to allow for what we call Wilson plaquette operators. So essentially, it's like the magnetic flux that winds around one of these green plaquettes is the product of the weight for Pauli C operator, and this plays the role of the magnetic field. So they compete with one another, and the important thing is that they have a local gauge symmetry. So this Hamiltonian, it commutes with an extensive number of symmetry operations, which are what we call the star operators. So these are just around each side of the lattice. You have the product of 4 Pauli X matrices, and you can easily see that this commutes with both the electric and the magnetic field term. So there is the equivalent of the Gauss law, which would be the gradient of the electric field is equal to the charge. Here, the equivalent of the gradient of the electric field is just the star operator, and it has to be equal to the charge. Since there is no charge, this is just equal to +1. So this is what we call in quantum information, we call this a stabilizer state. Okay. So the nice thing of this field theory now is, as opposed to the U1 Maxwell equation, where I have like fixed constants of nature, this vacuum permittivity, right? Here I have a free parameter that I can play with. Is what we call the electric field. It comes with H, but it's not Planck's constant. And when you tune it, then you can go from a deconfined phase towards a confined phase. So there is a deconfined phase transition that connects a confined phase to something that is topologically ordered, as we now understand, phase where there's long-range entanglement, there's topological contribution to entanglement entropy, and so forth, and so on and so forth. And this is actually where very much related to toric code quantum error correction. This is the phase where you do quantum error correction and code qubits in non-local properties that are kind of robust to errors. So if you actually want to see this confinement, the confinement is much nicer to work with theories that actually have the matter and the gauge field. So the previous one, there was only magnetic field terms and electric field terms, but it's purely a gauge theory. There are no matter particles. If I want to put matter particles, then I have to come back to my idea of particles tunneling from one side to the other of the lattice and being mediated by a parallel transporter, right? That allows me to retain this this local gauge symmetry. So in this case, it's C2. So it's very simple. It's just the tunneling has to be mediated by a gauge field. It's just the C-type Pauli matrix, right? Now the Gauss law is modified. I don't have these star operators, but I have to incorporate also the density of the particles, right? Because this Gauss law is always gradient of the electric field equal to the density of particles, where here, since it's a C2 gauge theory, what appears in the Gauss law is the parity of the particles. If I have an even number of particles, it's like having 0 charge. If I have an odd number of particles, it's like having a 1 charge under this C2, right? And the kind of things that you can study, even in this one-dimensional simple system, is actually the fact that when charged particles move, they are also sinks and sources of the electric field. So they create electric field lines. So I have now here 2 particles with C2 charge 1. They create an electric field that is in this source, and then it dies at this sink, right? So there's an electric field line. And actually, in these 1D models, what you can see is the analogy of this confinement. So when the particles move, the electric field line grows, and then they see that it has to stretch, and you pay an energy. So actually, the particles, they don't want to go away from each other. So as you see in these DMRD simulations, where we put like 2 particles in this model, and actually you see them as they spread initially, they look like spreading freely, but actually after some time they realize that the electric field line is paying a lot of energy, so actually they collide back and they are confined, right? So how can we simulate this with our trapped ion systems? I was talking about at the beginning that these phonons, you can make them tunnel as if they were charged particles, but actually what we are missing is the gauge fields. So the gauge fields in this C2 gauge theories are qubits. So the nice thing is that in trapped ion systems, we not only have the phonons of the ions, but actually there is all the internal degrees of freedom, the electronic structure that we can use to put qubits in the system. So let me go back to this idea of the AC starships. It was a slightly, not very detailed, but actually when you work out the details, you get this AC starship by 2 beams that can, mediate some interaction via an excited state. But actually, this can be state dependent. So it might depend on the state up or down of your qubit. So actually, what you can come up with are a generalization of these AC starships that now depend on the qubit of your trapped ion, and actually by aligning the wave vector of your 2 laser beams, such that it's not exactly aligned with one of the trap axes, say X, Y, or Z, but you align it somewhere in between. Actually, you can start coupling different modes of the system. So it's like essentially like a parametric conversion, but now it will be state dependent. So what we were picturing or thinking about is actually what happens if I look at this trapped ion chain that can vibrate, say, along X or along Y, and I use these state-dependent parametric conversions in order to couple vibrations or phonons from this direction, this vibration, to that other direction over there. And you can convince yourself that when you set the bit note of your 2 laser beams to be exactly the energy difference of these 2 vibrational excitations, actually what you are able to engineer is the simplest model of this C2 gauge theory with matter, where essentially you have this parametric down conversion, this parametric frequency conversion between vibrations along Y to vibrations along X, but is mediated by the qubit with the C Pauli matrix, right? And if you detune it properly, it depends on the scheme, you can also engineer what would be the effect of the electric field, right? So now what we have in pictures in mind is like this kind of dynamics, right? That I have a vibration, a single phonon that is vibrating, say, along X, and now it will tunnel and it will vibrate along Y. But at the same time, this is correlated with the spin, right? The spin has to flip. So if it's in the minus state, right, due to the action of this C operator, it will flip into the plus state. And this actually has an interpretation of this electric field line stretching and compressing. So the analogy is perfect. Actually, you can describe the system as just in using the U1 symmetry global and this Gauss law. It's just a two-level system. And when you have a single charged particle, a single phonon, you can either put it on the left or you can put it on the right. So if you put it on the right, there has to be an electric field string that connects to the boundary of your system. So this is what is happening. It's just my phonon is tunneling from one side to the other. The electric field is stretching and compressing back and forth in periodic oscillations, right? So these were our simulations of the physical system, how we would develop these excitations, and you see perfect Rabi flops of the exchange of the excitation, and at the same time, the electric field is perfectly correlated. We then thought about, alternative ways of inducing this state-dependent hopping, if you want, or this gates invariant hopping. And actually, it's a much nicer way than what I said about AC star shift. You can use something that in ions they're using all the day to do trapped ion gates and quantum computing, which is state-dependent forces. So this is a force, you push the ion in one direction and it depends on the spin. And now if you use non-commuting terms of these state-dependent forces, actually what you see is that from the interference of these terms, you can get a term that is very similar. So it's like this state-dependent hopping that is gauge invariant, right? So we started modeling imperfections in the system and everything was looking nice. So the people at Oxford, they decided to do the experiment. But they then realized when doing the experiment that there is one thing that you have to be very careful about, and it's the fact that there can be additional noise in your simulation that brings you, it spoils this gauge symmetry, and that's quite important. So the simplest noise that you can think about is dephasing. So you might find phase flip errors that might have some time dependence if you want. And actually, this is very easy to see that this term does not commute with the Gauss generators of your symmetry. So you have to do something about it, otherwise you are not simulating a gauge theory, right? So if you can think about it in a sense, I told you that you can think about the stabilizers. So actually, my physical Hilbert space is kind of a subspace of the full Hilbert space where all the stabilizers have +1 eigenvalue. And this phase flip error brings me out of it. It's the same business as quantum error correction. So you would like to measure the stabilizers and then put the system back to it by applying some correction. But when you think about that, actually, these stabilizers are very complicated because they're correlated functions between the bosons and the spins. So the other thing you could do instead of quantum error correction is some quantum error suppression. So you can do a spin echo type of evolution, right? You want to refocus the field, so you need to apply a pi pulse at the middle that reverses the effects of the space flip. But actually, you have to be careful because if you do that, then you are also reversing the tunneling. So you have to do spin echo that also reverses one of the phonon operators, such that the tunneling is also reversed and everything is gauge invariant, right? So this is what they did in the experiment. They can apply pi pulses to the qubits, but they also can control the phase of the tunneling strength. So by doing this at the same time, breaking the time dynamics in two, they were able to refocus the effects of a dephasing noise, but not kill what would be the C2 gauge theory. And it worked very nice. So as you can see in these pictures here, this is again the exchange of these phononic excitations between X and Y axis. And as you can see, it's perfectly correlated with the spin. So you're seeing the electric field stretching and compressing just as the charged particle, the C2 particle, tunnels back and forth. This is very nice. You can actually start playing with this electric field. Now, as you put the electric field, you're penalizing this compression and stretching because you have to put an energy, right? So this is a detuned Rabi oscillation, and they were able to see, again, that the particle, depending on how much you detune from the effective zero, it stops moving. It's essentially confined if you want to see it in this toy model, right? So as you move along this axis, the oscillations, they have a much lower visibility, and actually their frequency is increased. And this is again correlated between the vibrational excitations and the spin. So what else can we do? Actually, what you'd like to do is not just a single link, but you'd like to move forward. So what next thing you can do is a loop. So for instance, if you have now 2 ions instead of 1, each of these vertical links, it will be a C2, state-dependent hopping. But in order to build a full gauge invariant model, you're missing these 2 other links over here, which are just given by dipole-dipole interactions, and they are not negated by spin. What you can do is a sort of dimensional reduction. So when you work with collective vibrational modes, so this would be like the center of mass modes of these two ions, And actually with that, you can effectively create like a tunneling, which is gauge invariant, and there is a loop in between. This is very nice because by having a loop, you have the other ingredient that was missing in the system, which is the magnetic excitations and the magnetic fluxes, right? So there can be now closed paths in these synthetic lattices, and they're pierced by a magnetic flux that is now dynamical. And this brings us to the next part, the next effect that I want to discuss, which is, Aharonov-Bohm interference. So the fact that the fluxes can be zero when the spins are parallel, or the fluxes can be pi when they are antiparallel. This means that the particle, when it's pi, there will be destructive interference, it cannot tunnel. And when it's zero, there is no interference at all, so it can tunnel, right? So actually, in order to understand that perfectly with gauge symmetry, what you have to understand is that in this magnetic field basis of fluxes, zeros and pi's, actually you have to deal with bell pairs, essentially. So entangled states of the spins. They can either be combinations of parallel spins, up, and down, or the antiparallel ones, right? And depending on these two, the excitation that you put in one side 1 to 0, you can tunnel to side 0, 1, or the other way around, right? So this they were also able to do in the experiments. Actually, it's very nice. So it brings tools of quantum computing with trapped ions because they can create these bell states with reasonable fidelities. And actually, what the new part is that you can create these bell pairs, but at the same time, you create a single phonon excitation. You apply this state-dependent forces that lead to this effective gauge theory. And you see exactly what I was saying, right? So when you start with one of these bell pairs that is a pi flux, essentially the excitation do not have any dynamics because there is a Aharonov-Bohm interference. Whereas when they are both of them in up, or down, then there is again like this periodic exchange of the particle. And now the nice thing is that the flux is also in a sense responding to the gauge field is responding to the dynamics. So actually, what you are seeing here is that the correlations in the gauge field, whether it's in a bell pair which is phi plus or phi minus, it is also evolving periodically with the same periodicity as the charged particle. So where can we go from here? We can start dreaming because we are theorists, and then we can think about scaling, right? So essentially, what we work out in the theory paper is a way that you can start playing with this center of mass modes in two different directions, thinking about chains, not just links. And actually, there is a way in which you can go to a full 1D chain. You can see the details in the paper, but this would allow us to see these plots of confinement in place, where essentially by increasing the electric field strength, you can see how the particles are more or less confined. They are always oscillating periodically around the positions where they started with. So the last part of work that I want to comment on briefly are generalizations where, this physics of the 1D model is interesting. You can test confinement, but what you cannot test is deconfinement because it's just a 1D model. So you need to go slightly beyond that. So what we started thinking about is change of loops. Now you have this magnetic field term, and you can start thinking about the competition between the transport and the magnetic field interactions and electric field. So this is the model that we have been studying theoretically. It's just a chain of loops, as I said. And what you can include in the model now is like these placket operators. Now they are very simple. It's not wait for C operators. It's just CC operator. And you can start seeing what is the physics of this model. So what you realize is that all the interesting parts, they develop in what we call the triplet subspace. So it's like the combination of these three bell pairs only. And actually the Gauss law you can express it as if it was spin 1 gauge theory now. So the nice thing that can happen now is that when you start playing with this magnetic field interaction strength, the physics of the matter changes quite a lot. So if the interactions is negative, for instance, then essentially what you get is a change where everything is zero flux, and your particles, if you're at a certain filling, such as 2/3, then they will want to spread uniformly around this lattice, right? But now you go and increase your capital J, and then you go to other phases. So for instance, you can go to 1 where you have to divide your particles in bunches of 2 particles. And then these are, just distributed in 3 sites. So essentially, there are like a configuration of 0 and pi fluxes. Whenever you have a pi flux, you disconnect the chain into different trimers, and then you distribute your particles within the trimer. As you go increasing J, you can go to other situations where actually, instead of trimers, what you have is dimers. So you have now just 2 sites that are disconnected from everything else, and then your 2 particles, this is very simple, they would just go to one side or the other side of your dimer, right? So you can start seeing phase transitions. This is purely classical, sorry, so this is only playing with J, but my electric field was 0. Now, when we start thinking about introducing quantum fluctuations, then things become much more interesting, because these dimers and these localized particles, they can start moving, right? For instance, if I have one of these dimers over here, the electric field, what will do is that it will flip this pi flux to a 0 flux, and now the particle has more space to tunnel. So in a second order process, it will tunnel over here, and then tunnel back, and then you're seeing like the particle moving. So this maps into a Bose-Hubbard model, and what you can prove is that your particle is still in a what we call a Luttinger liquid. So it's a gapless phase, and actually this gapless phase connects completely as you go from H perturbative to H very large. It's a Luttinger liquid where the phases are purely confined, but the nice thing is that the excitations, they're made by mesons in a sense, so it's like 2 particles sitting together and moving freely in your lattice. What we discovered when doing the numerics is that actually there is a new thing. When you increase the quantum fluctuations and the magnetic field strength, there's a new phase that appears at intermediate positive magnetic interactions. And this is kind of a mode insulator. So I told you about these trimers that you put 2 particles. Actually, they cannot move. They're very, the lattice is fully packed. And if you try to put an extra particle, there is an energy gap. So what I'm showing here is this energy gap that is related to the particle gap. And so this is what they call a C3 mode insulator, because the entanglement entropy, it has a periodicity of 3 sides. So there is only correlations when the particles can tunnel in your trimers, but not when there is a pi flux in between. And the last thing I want to touch, and with this I finish, is the fact that, as I was telling you at the beginning, whenever you have some interplay between magnetic field terms, electric field terms, and dynamics of charged particles, you can have not only confined phases, but also deconfined. So if I start my system, the parameters of my system over here for a kind of strong electric field term and a negative coupling strength, actually I put 2 excitations in my system, and I see again the fact that they start spreading, but at some point they see the electric field line that is created in between, and they decide to refocus again. Now, if you go approaching the critical line, you see that this light cone excitation, light cone behavior, in a sense, it spreads slightly longer, but at some point it will start refocusing, so it's still confined. What we found out actually is that if you go to a certain parameter regimes, you find perfect light cones. So there is the confinement, and this we have also checked with by just computing like the decay of the Gates invariant Green's function, and it shows perfect power law behavior in this case. So this shows that just the single C2 charges, they are actually deconfined, and this is a very complicated interplay between all the physics that is taking place, like the magnetic interaction, the flux, the electric field, and the Gates invariant tunneling. So with this, I would like to conclude by saying that there is this dream in this community that we will be able at some point to study like really quantum field theories in the large scale with these quantum simulators. And my take on is that along the way, we will be still playing with toy models for quite a while. So let's enjoy the ride, and let's provide like some interdisciplinary look into these old problems. Thank you very much.
Thank you, Alejandro. Thanks a lot for a nice talk. I really didn't much time, but maybe for one short question. Okay, Javier, I hope you can hear us.
To be honest, like it's very hard to listen. Yeah. Okay, perfect.
Okay, I can speak directly to you, maybe. So my question is, it's just very short. So do you see any prospects of generalizing this scheme to higher symmetry gauge fields or non-abelian fields? using this platform, and what are the challenges in this case?
I think for me, it would already be super nice if we were able to scale in the experiment to larger system sizes, but dealing with this simple C2 gates theory. And this is already a challenge for trapped ion system. Maybe there are other platforms where scaling is simpler, because I think that these ideas, they are portable to other platforms. If you're interested into really simulating non-abelian gauge field theory, there are a lot of theory works that have been proposed, and to my knowledge, this is still very challenging. Especially, like, one thing that I did not emphasize is that there is a lot of progress in this digital quantum simulation, where essentially you have gates and you just concatenate them in a Trotter expansion to do gauge field theories. And actually, I think that there are already results on some non-abelian aspects of it. But actually, in this, we are interested in analog quantum simulation, where you have really a Hamiltonian and everything works in continuous time, and that is way more complicated. So just doing a Placket term in the Hamiltonian approach is very complicated. So let alone just going to non-abelian gauge field, I think it will be super complicated. But anyway, there's progress, and hopefully there will be more clever ideas than ours. And
okay, thanks.
So thanks, Alejandro, once more.
Thank you so much.
okay, thank you.
Should we test the mic? Yeah.